Hi, good day to Dr. Shamila. My name is HENG, matrix number 302233. My group consists of CHEONG Jen 301803 and Johnson Lee 300337. So my group will be presenting about the differential and integral calculus of function of several variables. Alright, so let's quickly go through the agenda. So we have introduction, brief overview, illustration of theories and laws, demonstration, and lastly conclusion. Okay, so what are the importance of differential and integral calculus of functions with several variables, right? So we all know that calculus is very important in our life, but what are the importance of it being having several variables? So it extends the concept of single variable calculus to higher dimensions. So one variable will have one dimension, with another variable at another dimension, and another variable equals another dimension, and so on and so forth. So it allows us to analyze more complex multivariate systems. It is also essential for modeling real-world systems such as temperature distribution, flow of fluids, economic models that involve many variables. And lastly, it is the basis for advanced mathematical theories such as differential equations, optimization, and vector calculus.
How can we apply differential and integral calculus of functions of several variables? Well, for instance, in physics, we can use divergence to analyze electric and magnetic fields, Stokes' theorem to understand fluid flow, and gradient vector to model temperature distribution. In econs and finance, we can maximize profit and minimize cost with constraints using Lagrange multipliers, as well as modeling price derivatives using partial differential equations. Besides, partial differential equations can also describe how populations change over time and disperse in space. Differential and integral calculus also helps in enhancing clarity in medical images.
Alright, now let's go through the brief overview. The differential and integral calculus of functions of several variables extends the ideas of single variable calculus to functions that depend on two or more variables. So it is crucial for analyzing systems where multiple factors are at play simultaneously. We can label them as x or y or z depending on how many factors are involved. Right, so the first concept we have is the partial derivative. We've learned that in classes, and the simplest way of saying it is that we can differentiate with respect to either variables. So let's say in this example here we have a function with x and y variable. So a partial derivative would have a fx, which is f differentiated with respect to x, and fy, which is f differentiated with respect to y. So this will be called the partial derivatives. So in the definition here, we have partial derivatives represents the rate of change of a function with respect to one variable while keeping others constant. Differentiate x, keep y constant. Differentiate y, keep x constant.
There are two concepts of multiple integral here. Let's begin with iterated integrals. With iterated integral, we can evaluate multiple integrals by breaking it down into many single integrals. Now, suppose f is a function of two variables that is continuous on the rectangle R that has a range AB and CD. Suppose AB lie on the x-axis and CD on the y-axis. As you can see here, for a double integral, the iterated integral can be written in two forms. In the first form, we first integrate with respect to y, keeping x fixed. Confirm the integration order by checking the range applied in the integration with respect to y. Then, we can integrate the resulting function with respect to x. The order of integration is interchangeable, but always make sure the range we apply to it is correct. Iterated integral allows us to compute the volume under the surface defined by the function f over the rectangle R. Next, let's explore triple integrals. Suppose f is a function defined on a cuboid B with specified boundaries. The triple integral of f over cuboid B would be the formula shown here. If the limits exist, the volume under a surface in a 3D space can be computed as a triple Riemann sum of this small volume element denoted by delta V. According to Fubini's theorem and the iterated integral concept we mentioned earlier, f can be integrated in any order as long as the integrals are finite and the ranges are correct. Now, to wrap up, multiple integrals extend the concept of integration to functions of several variables. These key concepts is crucial for applications in many fields, especially engineering, as we will see later in the example questions.
Now let's move on to the third concept, which is vector fields. By definition, a vector field on 2 or 3-dimensional space is a function f that assigns to each point x, y, or x, y, z, which is 3-dimensional, a 2 or 3-dimensional vector given by f, x, y, or f, x, y, z. So what does this mean? Isn't this just a function? Right, so how does this vector function differ from our ordinary functions? A vector has direction and magnitude. Let's look at the image above is function vector f, which with x, y has p, x, y, I plus q, x, y, j. We can imagine it as 2-dimensional plane, right? So P is one point, xy, and Q is another point, xy, where when they connect together, it forms a function which has a length, which is the magnitude, and there is also a direction. Similarly, f, x, y, z is basically the same thing, but there's just another dimension where the arrow not only travels flat, front and back, left and right, it also goes up and down now. Similarly, there is length, where there's now 3 points, and then you just go up. Then there is magnitude, because there's length, and there is also direction. So the image on my left here, I think, it also shows the vector field inside a cube region, which is three-dimensional.
Next, we will talk about gradient. The gradient is a scalar field measure the rate and the direction of the steepest ascent and descent of the field. It points in the direction of the greatest rate of increase or decrease of the function. For the gradient, we usually write in the formula f equals to I times with the partial derivative f respect to x plus j partial derivative f respect to y plus k partial derivative f respect to z.
We have here the divergence theorem, also known as Gauss' law. The divergence theorem relates the flux of a vector field through a closed surface to the divergence of the field inside the surface. That means the divergence of a vector field measures the magnitude of a source or sink at a given point. Alright, let's look at the right-hand side equation. The A underneath the integral represents a surface of any 3D body, and the circle at the center of the integral tells us that the surface of the 3D body must be closed. The integrand f represents a vector field, hence a 3D body should have a vector field of 3 components, which are fx, fy, and fz. Lastly, dA is the small surface element that is a vector with a magnitude and a direction perpendicular to the surface as seen in the diagram. It is similar to the vector field f. Now remember, the dot product of two orthogonal vectors always yields 0, but the dot product of parallel vectors exists as a non-zero scalar. Hence, every orthogonal vector field is cancelled out, leaving only the vector field parallel to the dA element that could be directed outwards or inwards from the surface of the 3D body. The integral as a Riemann sum hence adds up all the dot product of vector field and the dA across the surface. This is known as the flux phi of the vector field through surface A. Now, let's take a look at the left-hand side equation. The V underneath is the volume enclosed by the surface A, while dV is a small volume element. The dot product of the nabla operator and the vector field F gives us the sum of the derivatives of F with respect to the space coordinates x, y, and z. This product is known as the divergence of F. The divergence can be computed at any point x, y, z of the body. In this case, a positive divergence indicates a source, where the field is emanating from, and a negative divergence indicates a sink, where the field is converging to. Gauss' theorem says that the sum of divergence of the vector field within a volume is equivalent to the total flux of the vector field through the surface of that volume.
Now let's look at Stokes' theorem. Stokes' theorem is a bit similar to Divergence theorem. However, in Divergence theorem it's dot product, but in Stokes' theorem it is a cross product. Right. So now let's look at the first image, which has a function that's going on here. Right. So on the right hand side, it's a closed integral, which is which consists of f, which is a vector field f, and dl, which is a line element that exists in a closed loop. The dl, which will have a magnitude and also a direction. Now, f vector field will have a parallel and orthogonal element. However, line element only travels in a closed loop. Only vector field which travels along the line element is considered in this scalar product. So the orthogonal vector field f would be neglected, and we only take in the parallel vector field f. And the scalar products for each location on a loop are summed up using the integral. Now look at the left hand side of the equation, which is also an integral, but this time it is integrated towards a area, surface area. Similarly to Divergence theorem, it is a closed volume, but in Stokes' theorem it is a closed area enclosed by a loop. Right, it's a bit open, but it's still like a closed area enclosed by the loop. Right, so in the left hand side here we have the nabla operator crossed with the vector field f, and it is differentiated against a surface. So dA here is a surface element on A, which can be any size, and it is orthogonal at any surface location. So the cross product between the nabla operator and the vector field f is called the curl of the vector field f. Right, so the result is another vector field which shows how much field f rotates around a surface A. So as you can see in the image there, we have the small little square surfaces, and the green arrow represents the curl, and the result of the nabla cross with vector field f is how much it rotates around the surface. Similarly, the cross product for each location is summed up using integral, so both left hand side and right hand side should be equal according to the theorem. And the next image here, we can see more detail of what a curl vector field f looks like. So nabla operator cross with fx, fy, and fz, and we will get the following equation.
Next, let's look together with the question gradient. From the question, we know that the race engineer try to determines the coolest spot of the tire to adjust their strategy to heating up the tires evenly to ensure the optimal racing performance. So from this question, we found that there's given the x t equals to x power of 4y minus 2x power of 3y power of 2 plus z square, where x, y, z equals to 5, 4, and 7. So after that, we find out all the information and we find out all the things that we need to use in the formula. There is partial derivative t respect to x, there is 4x power of 3y minus 6x power of 2, y power of 2. Partial derivative t over respect to y, there is x power of 4 minus 4 power x power of 3, y. And partial derivative t respect to z, there is 2z. After having all this information, we sub into the gradient formula gradient. There is gradient vector t equals to 4x power of 3y minus 6x squared y squared times I plus x power of 4 minus 4x power of 3y times j plus 2zk. So after that, we find the gradient at 5, 4, and 7, and we will get it. The gradient is negative 400i minus 1375j plus 14k. So beside that, we need to find the negative gradient vector for the stimulus distance. That is negative t. That is 400i plus 1375j minus 14k. So to find the coolest spot on the tire, the engineer should move in the direction of 400, 1375, and negative 14. This vector indicates the direction in which the temperature decreased the most rapidly over the point 5, 4, 7.
Consider an oil spill in the ocean where the velocity vector field of the spreading oil is given by F equals to 4xz negative y squared and yz. Petroleum engineers want to determine if there are sources of spill within a specified closed region D in the ocean. Calculate the flux of oil through the boundary of region D, given D is a specified region in the ocean with appropriate ranges for x, y, and z. Now we know vector F is a vector that has three components. They are Fx, Fy, and Fz. First, we find the divergence of vector field F. We can do that by multiplying vector field F with a Nabla operator. The Nabla operator is a partial derivative. So we multiply each of the components with the partial derivatives of dx, dy, and dz. We differentiate each component with the respective partial derivative. So first fx dx will get 4z, and this one will get negative 2y and plus y. We'll get the divergence of 4z minus y. Now, remember that the total phi flux of the vector field through a surface, let's say A, within a region D is always equivalent to the sum of divergence within that region D. So we can write this formula. The volume integral here, we can write it as a triple integral so that we can input the values of the ranges later. So we'll write something like this. Now remember iterated integral Archimedes theorem earlier. Now we obey that and we input the ranges correctly with the integration order. 0, 2, 0, 2, 0, 2. Now they're all 0, 2, it doesn't matter in front. But if the ranges are different, then you have to take note. We write the divergence, we get 4z minus y. That will be our first function. dz, dy, and dx. We integrate the first function with dz. We'll get 2z squared minus yz, so 2 dy dx. We sub in the value for z, we'll get 8 minus 2y dy dx. We integrate the second function that we just got with y. So we get 8y minus y squared. We sub in the value for y, and we'll get 12 dx. And we integrate the last function with dx, we'll get 12x. Sub in the values, and we'll get a total phi flux of 24.
Alright, so consider a simple example question here for Stokes' theorem. We would like to determine the axis about which the angular momentum density is oriented and calculate the strength of the rotation of the gravitational field. So we are given the fx, fy, and fz, which is 2x, z power of 3, fy equals to 0, fz equals to 3x squared, y, and we just differentiate them accordingly, right? And then we just plug it into the curl formula, and we will have the axis which it rotates, where the rotation happens. So we put in the point 2x, 0y, and 3z. So we get that the curl of gravitational field F at 203 is 12 negative 108 and 0. Right, so the magnitude of rotation of one curl is the square, and the square plus square plus square square root, and then you get the magnitude, right? So we get 12 square root 82, and the direction of curl is along the xy plane because z is 0 and the positive x and negative y, and the strength is 12 square root 82. So as you can see here, the question is doesn't involve integral here because we are only working with one point, which is 2, 0 and 3. So we involve integral when there are several areas which involves like a enclosed surface. Then we will need to use integral. For this one, it's a point, so all we need to do is plug in the values and calculate the magnitude accordingly.
So, for the topic that we choose, that is differential and integral calculus, we explore the key concepts such as partial derivative, multiple integral, and vector fields. We also demonstrate the application through the example, like gradient, divergence, and curl. For the gradient, there is a model of rate of change in the temperature and pressure using the partial derivative, and divergence helps us to understand the behavior of electric and magnetic field using the multiple integral according to the Gauss theorem. Last but not least, curl aids in the understanding of rational aspect in a fluid flow with vector calculus. That's all from us. Thank you.